Okay, so welcome back. So we'll have Carolyn's second lecture.
Yeah, so last time we talked about SPTs and how to detect them from the boundary anomaly and also from properties of their defects. And today we're going to continue studying 2+1D SPTs. Last time I mentioned these two SPTs in 2+1D was Z2 symmetry, which is given by, so all of the P's are vertices of this lattice, and so we were comparing two different kinds of paramagnets under the Z2 symmetry. One is this very simple one, which is just a poly X operator on every vertex, and then this other one is a bit more complicated. It's a poly X operator, but it's decorated by all of these operators that act along the links around this plaquette. And at the end of the last lecture, I wrote down a boundary representation of the symmetry. So this was Z2 symmetry in 1+1D. And this boundary representation of the symmetry took a rather interesting form. You can write it as this. So this A is some big disk, and the boundary representation of the symmetry acts on the boundary of the disk. And it took the form of something like this. And we also showed that there's a way to extract from this representation of the Z2 symmetry a 3 cocycle. And the idea was that if we take this, it acts on the entire disk, but we can restrict it to an interval. Maybe instead I should call this guy A. So this is just your boundary. I'm going to call you boundary A the restriction of the symmetry operator to this patch. And then what we found was something like this. So, of course, the entire operator follows a group law, but if you restrict it to an interval, it only follows a group law up to this guy, which is an operator supported on the left and right ends of the interval. So this is equal to omega left, G, H, tensor omega right, G, H. And then we showed that this operator satisfies if you consider the composition of 3 group actions. This operator satisfies something like this. However, if we just take the left or the right side, then we get this up to a phase. So if we just take, say, the right side, then this is only up to a phase. And then we showed that if you then compute this guy for this representation of the symmetry up here, you get a phase of -1 when G, H, and K are all the non-trivial element of Z2. Okay. So as Sal mentioned yesterday morning, in the 1+1D case, we were able to study this 1+1D boundary anomaly, which is a projective representation 0+1D, from both considering the system with an open boundary condition or in the bulk using symmetry defects. However, for other kinds of SPTs, for example, for this 2+1D SPT that I'm going to talk about today, we're going to consider not only symmetry defects, but also symmetry fluxes. And the idea is that, so as I mentioned last time, if I consider the system, well, okay, maybe first I should mention what is a symmetry flux. As I mentioned last time, if you have a system in, say, 2 dimensions, or any dimension, then the symmetry defect is a codimension 1 defect. So if I have a 2-dimensional space, then the symmetry defect may live along a line, and it contains the G action on the left-hand side. Now, symmetry.
When you think of this, do you think of that's where your spin lattice lives, and there's an additional time direction, or is it already space-time?
This is just space.
Okay.
Yeah. So you can think of this as there's also a time direction if you want, but this is going to just be my spatial lattice. Now, symmetry flux is where the symmetry defect ends. So the symmetry flux is the endpoint of the symmetry defect. For example,
Sorry, what's the meaning of this shaded in there?
there's still a G symmetry action. So if you kind of go around the symmetry flux, you'll pick up the G symmetry action. Okay, so last time we mentioned how in a Hamiltonian kind of lattice model, a way to insert a symmetry defect is as follows. Let's call this region A. And this is specifically, for example, if you consider periodic boundary conditions, this region A is some patch of your torus, and then this region B will be some other patch of your torus. And you just need a larger than the range of your Hamiltonian terms. And what this does is, this guy inserts a G and G inverse defect, and the purpose of this guy is to remove the modification of H near one of the boundaries. So then you're left with a single symmetry defect. So now when you want to end the system, it roughly looks like this. Suppose that I have a spatial lattice in 2 dimensions. If I wanted to have a symmetry defect, then I would have the Hamiltonian terms kind of modified all along this line. Because when I conjugate the Hamiltonian in the, say, lower half space, then all the Hamiltonian terms are symmetric, so all the ones fully supported in the lower half space are left alone, but the ones that straddle the boundary may be modified. And when you insert an extrinsic defect, then instead of modifying it along this line out to infinity, you end this modification at certain flux insertion points. So a simple example of how this could happen is if you had just an Ising Hamiltonian, which we saw in the morning in Zohar's talk, where H is just the sum of nearest neighbor terms, and your global symmetry is a product of all of the poly X operators on all of the sites, then you can see that if you take this region, this lower half space to be your A, then if you just conjugate the Hamiltonian by U restricted to this lower half region, you'll flip the signs of all of these ZZ couplings, And a symmetry flux is when you end that flipping. And so now here, all of your ZZ couplings will be plus, but all of these will be minus. And all these above will be plus. So you kind of flip the couplings along a finite line. And now you can see that if you multiply all of the couplings around this line, you'll get, and you've inserted a Z2 symmetry flux because you'll have product of all these couplings being -1. So Z here will be -1, +1, +1, +1, and that's indicating that you've inserted a Z2 fluxer. This line is topological, you can move it, but these fluxes are not topological, you can't move them. Okay, it will be useful for us to, and I didn't mention this yesterday, but it's kind of important to note that the defect Hamiltonian is not unitarily related to the Hamiltonian without the defect. In particular, they can have different spectrum in general. Okay. It will be useful for us to consider how to insert defects on a wave function, because that will be related to the idea of braiding symmetry fluxes along on a wave function. So if I act with the symmetry restricted to a patch, so I act with product of PXD here, on my wave function, on my ground state wave function, and we'll consider all these Hamiltonians on periodic boundary conditions, so you have a unique ground state, and you can act with the symmetry action on a patch. And because these wave functions are symmetric under the symmetry, the action of the symmetry on this patch, you can dress it so that it has expectation value 1 in this state. And so what that also means is that the action of the symmetry restricted to this patch on the state is equivalent to the action of a 1D operator on this state. So in this particular case, you can see that it's maybe not obvious, but you can see that all of these Hamiltonian terms will be minimized by your wave function. So they have expectation value 1 in your wave function. And if you multiply all these BPs for a large region, then all of these dressings along these edges will cancel in the bulk of the region. And so you really just get a product of x in some large patch dressed by some string operator. So the product of x for some large patch on your wave function is equal to some string operator on the boundary of the patch on your wave function. And it turns out that you can view this as kind of a closed flux insertion operator. The point is that this is a local unitary operator. So you can truncate this guy. So let's call this WGA, and this is going to be UG on the patch. So you can write WGA equals WGA left, WGA right, and then if you multiply the WGA left onto your product restricted symmetry operator, then that has the same effect on your symmetric ground state as WGA right. And now this is an open flux insertion operator. The reason is this operator is only supported on this branch of this branch. And so it leaves the ground state invariant on the left side. So this just looks like the ground state on the left side. But you also know, because this is equivalent to having the symmetry action in this disk, that if you go around this guy, you get acted on by the symmetry. So this is like a physical way to implement flux insertion. And it turns out that this flux insertion operator, this WG, is also a 1D operator. And it also forms a representation of G. And it forms the same anomalous representation of G as this boundary representation. So what that means is that everything you do with this U boundary of G, you can do with this bulk flux insertion operator. And so what this means is, in this case, in order to calculate the 3 cocycle, we had to take a restriction of this 1D operator to an interval. And that corresponds to considering this open flux insertion operator with these 2 endpoints here. Okay, so that means that similar to how we can obtain this W minus 1, minus 1, minus 1, minus 1 being the non-trivial element of Z2, we can compute it from this boundary. We can also get it completely in the bulk on periodic boundary conditions once we write down this flux insertion operator, which we can do. Yeah?
Is the notation actually on
So this notation is saying that within this disk, we're going to act with the symmetry. So the symmetry acts on all of space, but we can restrict it to a disk. Now, the action of that symmetry restricted to that disk on the symmetry is equivalent to this loop operator acting on your ground state. And so if you want to have a line operator such that crossing through the line operator acts the symmetry, and it also leaves the ground state invariant on the left half of space, so it's invisible on this part of space, then this is one way to construct such an operator. Yeah.
In order to say that the operator acting on the boundary circle will be a product on the left and on the right, here I guess it makes sense if the operator is a constant depth circuit. Is it always the case under conversion?
Yeah, so there are certain cases where it may not be a fine depth circuit. Whenever when you are having a 2-dimensional space, so a 1-dimensional flux insertion operator, this is always the case. But yeah, because you can classify 1D locality preserving unitaries, you know it's locality preserving, and then in this case it can always be written as a fine depth circuit, or like more generally a locally generated unitary. Okay, so but now we want to, so this is saying that what this is doing then is you have 2 group elements, boundary representations of the symmetry, because we want all these group elements to be the non-trivial guy. That means that the analogous kind of thing that you're doing here is you're taking this open flux insertion operator and squaring it, and then you can compute a 3 cocycle from that. This is all related physically to properties of fusing symmetry fluxes, and then you get this minus sign. But we want to relate it to braiding, because eventually we want to see that this is somehow related to braiding of symmetry fluxes. And the theory of braiding of symmetry fluxes is, in the mathematical language, is this G cross braided tensor category. It's the case where, so G cross braided tensor category is describing a 0-form symmetry together with 1-form symmetries. But we're going to consider the case where the 1-form symmetries are actually trivial. So we're just talking about 0-form symmetries and the symmetry defects and their fluxes. And one thing you can show is that there's this gauge invariant property. So that holds for any Zn. So So whenever you have a cocycle, which is describes a cohomology class, H3 of G, where G is Zn, with coefficients in U1, you can show that there's this gauge invariant quantity. Even though this is not well-defined up to coboundary, you can show that whenever you modify this by coboundary, all those cancel if you take the product of all these guys. So this is kind of gauge invariant quantity. And you can actually show that these fusion properties of the symmetry fluxes have an interpretation in terms of braiding of the symmetry fluxes. So how do you do this? The simplest way I know how to do this is using the heptagon equation. So the heptagon equation, many of you are familiar with hexagon equation. The heptagon equation is roughly the same as the hexagon equation, but it has an additional step because the symmetry fluxes come with the bulk symmetry action.
Sorry, but Carolyn,
Yeah.
is the breaking of the symmetry fluxes well defined? Is that itself gauge invariant? Because I thought like, they have some action on themselves. Can you define the braiding?
Yes, so there is a way to define braiding of symmetry fluxes. I'll show you shortly how to.
But it's gauge invariant.
In general, no, this RGG is not,
Yeah.
but when you take a product of n of them, it's gauge invariant. Yeah. And in general, you will have other indices, but all these symmetry fluxes that I'm dealing with are kind of abelian, so there are no other indices.
Sorry, what is this capital N again?
So this is if you have but the simplest case is when n equals 2, and in that case you have omega G1. G, this is the generator in this case. So this is equal to 1, this is equal to minus 1. That means that there's the braiding of the symmetry fluxes with a phase of minus 1.
Does this formula generalize to other groups? Like, so to me, the reference size basically like multiplying over some, like all the group elements in Zn. But if you replace Zn by any finite group G, do you expect a similar formula?
In general, if you replace it by any finite group G, this is actually not a gauge invariant quantity. But for Zn, this is gauge invariant. For other groups, there's other kinds of gauge invariant combinations of non-gauge invariant stuff. And so what this is saying is, okay, there's some connection between the properties of the fusion and movement of like these F symbols and braiding properties of the symmetry fluxes. And the way to derive this equation is to use the heptagon equation, which maybe I won't draw out the entire heptagon equation for you, but if you're familiar with the hexagon equation, it's roughly like this. The heptagon equation has one additional step, which is what's called a sliding move, U. So the reference for this is like Barkashli. This U move, and that's because for symmetry fluxes, unlike for one-form symmetries and one-form symmetry defects, they actually kind of detect this process. So if you have a vertex, then it detects whether you move it through the vertex. And that's because symmetry defects, these guys, for zero-form symmetries, they come with the symmetry action, so it can act on the vertex, and it detects this move. So this is the one additional step that you don't get in the hexagon equation. Okay, so then you can kind of see, because in this kind of equation, you can plug in omega for the F symbol in this G cross braided unit category where the underlying modular tensor category is trivial. And then you can write a relation between FFF and RRR. And so then if you work it out, you will find that plugging in this as F, you'll end up getting this equation. Yeah?
Is there a useful space-time picture to see why a patch of symmetry flux becomes just effectively a line? Space-time representation of time and place?
You mean a space-time picture for this?
Yeah, basically.
Yeah, so I guess one way to see it is this is in a symmetric phase. So this is a defect that can end to the vacuum. But you have to kind of dress it in order for it to end to the vacuum. So this is just kind of pulling the dressing to one side. The dressing is on the boundary. Does that answer your question?
Yeah, thank you. Yeah.
Okay.
So the vacuum omega is supposed to be invariant under the action of the entire WG. Something you didn't write, I believe. I'm trying to relate the top equation with the surplus to the bottom equation.
Oh, sorry, this is a W, and this is an omega. Is that a confusion? Or,
No, I don't think so. I'm still on the WG.
yes.
And the top equation is just the definition of this operator, which you split into two parts. But then you write that the left part acting on the vacuum equals the right part acting on the vacuum.
So this is saying that I'm splitting this into two parts. So now I'm going to pull the WGAL to the left side using the dagger.
But then the left-hand side, I thought, of the first equation is just the different representation of this operator, no? Because this seems to be like saying that WJ acting on omega equals omega, no?
So this is an operator. This is a big tensor product of operators acting on your state. And it has the same action as this
Yes,
boundary
same
operator
action,
acting on your state.
But then, is the vacuum invariant under this action? Does it equal to the omega or not?
I'm not sure what you mean by is it equal to the omega, because the omega is something that you compute by different combinations of this W operator.
I think the capital omega, so the vacuum state, capital omega, is not invariant under the action of the omega GA.
No, because this is the vacuum. If you act with this W operator, then you get, this is a non-trivial operator, right?
Yes, it's just another representation of the same operator. But then I don't understand the bottom equation, because if I move W left to the right-hand side, I seem to get, I get WG, so that seems to say that omega equals WG omega.
So I've only moved the part of this operator that's supported on the left-hand side to this left.
Right, but the left-hand side in the first equation still has something.
Yeah, this something is still here.
Something is still there.
Yeah.
Sorry. That's a stupid question.
Okay, thank you for the question. Okay, so I mean, there's something has to still be here, because you know that when you go around the symmetry defect, you get acted on by the symmetry. So the symmetry action is definitely still there. Okay, so so the way to get then the direct relationship between these three co-cycle and the symmetry flux braiding is using the heptagon equation. And also then more generally, you can also show for not only Zn, but like Zn cross Zn and other kinds of SPTs, you can relate properties of this symmetry flux fusion to symmetry flux braiding and symmetry flux sliding. And then once later on, we'll show that those are related to topological spins of anions once you gauge this symmetry. Which I was told that I should say gauging is the same as orbifolding. So for the people, this, the result of these two procedures is the same. Okay. Okay, as Matthew remarked, how do you actually braid symmetry fluxes? Because they do come with this bulk symmetry action, right? But there is a well-defined notion of braiding. The constraint that you have is you always have to be inserting these flux insertion operators, these open flux insertion operators on the ground state. So you have to be careful that you're always in the ground state. And so I'll just quickly sketch out how you might braid two symmetry fluxes. In the first step, we act with these two 1D flux insertion operators. And then in the second step, we want to move this guy around this guy, right? But if we want to do that, when you insert a symmetry, so if these are like, if this is the symmetry operator for a one-form symmetry, with these guys being the symmetry defects, then the only excitations are created at the endpoints. However, when this is a symmetry defect, or when this is a flux insertion operator, you create excitations all along this line. What you can do is you can get rid of those excitations by acting the symmetry in this lower half space. So you're also going to act, so the second step, maybe I should draw those separately. The second step is to interact with the symmetries. And now this part looks like the ground state, similar to what we had up here. Because it's a flux insertion operator composed with a bulk symmetry action. And then the third step is now that this looks like the ground state all along here, you can feel free to insert a flux insertion operator. So this is now WH. And the fourth step is now you're left over with a symmetry action in the bulk, so you have to undo it. And the nice thing is, now you can see that if you do these 4 steps, you can compare that to the procedure where you first just insert this B symmetry flux, and then you go ahead and insert the G symmetry flux. And so in equation form, it looks something like this. This is just kind of technical, but if you want to do it concretely, this is what you would do, but you don't need to pay attention to the details if this is too microscopic. Okay, so it's a well-defined procedure to braid symmetry fluxes, and you can see that in addition to making sure we always inserted the symmetry flux operator in the local ground state, here you also see that once you go around the symmetry flux, you pick up the action of G, right? Why did I want to go through this? Well, because now we can see that if you do this calculation, you can just do it with the concrete operators that we've written here, because with this Hamiltonian, you can get an explicit form for this WG and everything, and you can explicitly compute this and show that this is also equal to -1. Okay, now we can use this to do our gauging. And there are kind of 2 ways to do gauging that I'm going to talk about today. One is just kind of purely algebraic. It's just a map from properties of the symmetry defects and symmetry fluxes to properties of the anions that you would get. And by anions, I mean the spontaneously broken one-form symmetries of the resulting theory after you gauged. And another way is to do gauging explicitly on the lattice, and we can show that those produce the same results. In particular, after gauging these 2 paramagnets, we'll get 2 explicit forms for string net models that realize different topological orders.
So this product of ours is gauge invariant only in the Z2 case? Or?
Yeah.
Okay.
Yeah. This guy actually should be, it's HG and GH. So this
So that'll be the S, the angle, that'll be the S.
for abelian guys, yeah.
But again, will that be gauge invariant if it's not Z2?
Yeah, I think that for this guy, because it's just a phase, that should cancel between these 2. That would be the gauge transformation.
Oh, okay.
Yeah.
It's a symmetric product.
Yeah, exactly. But for more, like, this guy by itself is certainly not gauge invariant.
Although up there we're taking GG, so that was a symmetric combination. We had to take it to the nth power, right, to get something gauge invariant. But the big movement is not right.
Yeah, it might be the case that, well, that's the only way to relate it to this product of 3 cocycles. So there's no direct relationship between a single R and some product of 3 cocycles that I'm aware of. Okay, so, yeah.
And is this in the Barkashyan paper? Is this as well?
So the Barkashyan and L paper have the heptagon equation, but they may not say explicitly that you can use the heptagon equation to derive this gauge invariant product of 3 cocycles and map that to this product of R symbols, which will give you gradient properties. But you can, it's a very simple calculation using the heptagon equation and using the fact that for these particular kinds of SPTs, you can choose a gauge where this U equals 1. But for more general SPTs, you can't choose U equals 1.
What about this thing you just wrote as the reference for this?
This guy? Yeah, so, okay, you can look at my paper. I don't know if it was 2023 or 24, but it's this in one of the appendices of that paper. Okay. So let's gauge these SPTs, gauge the Z2 symmetry of these SPTs. And the Barkeshli et al. Paper tells us, okay, probably in the math literature you also know, but as a physicist, this is the paper that I read. If you know certain properties of the symmetry fluxes, we can get properties of the anions that we get after gauging the symmetry. So in particular, in their prescription, all of the anions that result from gauging a zero-form symmetry are of this form. There is a pair. What this is an orbit under the symmetry. So you start off with a G-graded category, and then you look at the orbit under the zero-form symmetry. And then you look at, so this is going to be orbit under G. So, and this is, I'm just going to define it as, so Europe of this kind of centralizer. So you have some orbit, you pick some representative element of the orbit, and then you look at the centralizer of that in the group, and then you look at Europs of that. So this is going to be an Europe, which may be a projective representation of the centralizer of the representative element. So in the usual case, where you don't have any topological order to start with, and you just have a G symmetry, then this is our familiar anion types, right? Because we have the conjugacy classes and Europs of like a representative of the conjugacy class.
You said it just now. By orbit, you mean orbit under conjugation.
Yes, of the G action. Yeah, exactly. So that means that after we gauge, we get a bunch of topological line operators that are labeled by this. And you can also deduce properties of these topological line operators. So for example, one thing you can get is that their quantum dimensions are just given in this way. And you can also get their topological spin. So this is just a character, which is the trace of this Europe. In the case where we're interested in, which is just Z2, so the reason why you have these two factors is you can think of this as a combination of a charge and a flux, essentially. And so this is the portion of the topological spin coming from the flux, and this is the portion of the topological spin coming from the Harnaff-Baum phase of the charge with the flux. Because the Europe is related to the charge. Okay, so you can see from this that this is actually quite simple when your group is Z2, which is what we're gauging. So in that case, we have two group elements. So we have two conjugacy classes. And each of them has a Z2 centralizer. And so what you can get is that this is the resulting data once you've gauged the Z2 symmetry. This kind of algebraic data. So for H1, this will map to the model that has been discussed many times. This maps to our code. Z2 gauge theory. In terms of the topological line operators, this has 4 line operators. So this guy is like the 1-1 element, where the conjugacy class is 1, and the irrep is trivial. This is the 1-1 element, where it's conjugacy class 1, and then irrep is non-trivial. And this is -1-1, and this is -1-1. And now you can compute the statistics as well, because these 3 are all going to have topological spin 1, because theta AG is 1, and then on the trivial irrep, the character is 1. So the only -1 comes from when you have a non-trivial irrep on a non-trivial group element, which is this guy here.
What is H1?
Sorry?
What is H1? So you take H1 and then you get the torque.
Oh, H1 is this H1.
Ah, so
Yeah.
thanks.
Yeah. So that H1 gave you some flux insertion operators and some symmetry defects. You run through this calculation, and you get just the algebraic data of the torque code. On the other hand, if you take H2 and plug in the flux insertion operator, you can do this calculation on the lattice. You can compute it using the 3 cocycle. What you get is H2 maps to double semyon. You have 1, and these guys, again, they have the same kind of labeling. However, because in this case, theta AG is equal to I, because we computed that the self-statistics of the symmetry defect is I, because the braiding is -1, so self-statistics is the square root of that. So this has theta S is equal to I, and this has theta S bar equals -I, because that also comes from a -1 of the non-trivial irrep on the non-trivial group element. Okay, and this has self-statistics 1, and this, of course, is self-statistics 1. Yeah?
So the gauging map took the IO of that lattice model and gave us an MTC here. But can we figure out what the lattice model is describing the toric code using this gauging?
Yeah. So that's the second. This is the algebraic gauging, and then you can also, of course, do gauging on the lattice, which we will now do.
Oh, okay.
Yeah. But this is just to say that now we see that this non-trivial 3 cocycle maps onto a non-trivial braiding of the symmetry fluxes, which then maps onto the braiding of these one-form symmetries. And so now you get 2 different modular tensor categories from these 2 different SPTs. Okay. So you should also notice that the charges are the same, but the fluxes are the only things that are different. Yeah?
So here, I would consider a general finite group, and we take a symmetry defect, we define theta of the A G. spin of the symmetry beta?
Yeah, so in this kind of procedure applies generally. So you could have any underlying modular tensor category, enrich it with some symmetry group, zero form symmetry, and then that will give you a G-graded category, and then you can then compute all of these pieces of data to get the resulting theory after you've gauged the zero form G symmetry. There's more pieces of data than just the ones I wrote down. But
Good.
yeah.
But you for this piece of data, I was wondering how you define data of A of G in general, not relating to. So are we computing using this formula and like convert it to the?
Yeah. So in general, you're given all of that data already, because you're given data of the underlying MTC and how you're enriching it with the zero form symmetry. So that's already kind of data that you're usually given. So like, for example, this is already data that you have. In this simple case, we just computed that data because we could get it from the 3 cocycle.
So in general, you just compute it algebraically because you already have the data rather than talking about the lattice model?
So in general, like it's kind of information that you're already assuming that you have in order to compute the properties of the gauged theory. Okay. Good. Okay, so now that we have kind of what we expect we will get after gauging the theory, let's see that we actually do get that theory in terms of a string net model when we gauge these H1 and H2 on the lattice. Okay, so I wrote down H1 and H2 over there, and we can gauge the global Z2 symmetry using a couple of well-defined steps. So the first step is to introduce U degrees of freedom, which are your gauge fields. So originally we're working with this triangular lattice. And our original matter degrees of freedom were on the vertices. And the gauge fields will be on the links between the vertices. So that's why I put mu PQ. So this is, say, P, and this is Q, and this is mu PQ. And so you can now act with poly operators, which are like mu X, Y, Z, on these qubits that are living on the links. And this is nice because these will give you one-form symmetries, like Sal talked about, where you really want these degrees of freedom to be on the one cells. The second step is to implement Gauss law. So the Z2 Gauss law that we'll have is XP is equal to product over Q. So this is like a Z2 analog of the usual Gauss law.
Sorry, Carolyn, what are the superscripts? What are the indices?
PQ is like the length between P and Q. And then this is the poly matrix index. Yes. We have this Gauss law that kind of fixes how spin flip will also affect the gauge fields. And the third step is to do minimal coupling. Because you're implementing this Gauss law, then you need everything to commute with GP is equal to XP product of Q, U, XPQ. So this is an operator that acts on this vertex and these 6 links. So you need every operator in your Hilbert space, every operator in your Hamiltonian to commute with that Gauss law operator. So in particular, you see that this BP operator doesn't commute with the Gauss law. So you need to do minimal coupling to make sure that it commutes with your Gauss law. And you can implement it when you set this Gauss law equals to 1. So that means that one way to do minimal coupling is to do you add the gauge field between your Ising couplings. And that will make sure all those operators in H1 and H2 will commute with your Gauss law. Yeah.
Can you just say again why you wanted to commute with that? Like, what's the relation between commuting with that and the Gauss law to the left of it?
Right, so this is our Gauss law. So we want to kind of implement this, be able to implement this on our Hilbert space. And if the operator doesn't commute, then it won't. Like especially like if you have a gauge field such that you have a Gauss law constraint, everything needs to be gauge invariant. And so this makes sure everything commutes with the Gauss law. Okay. And then there's one, I should mention that when you have Z2 gauge fields, there's the minimal coupling procedure isn't entirely unambiguous, but this is, but we'll sweep that under the rug. There's ways to make it unambiguous, more unambiguous. Okay, and then the fourth step is to implement zero gauge flux. So we want the ground state to have no gauge flux, because when we introduce these new gauge field degrees of freedom, they give us many, many different kinds of states with different gauge flux. If we want to isolate a ground state with zero gauge flux, then we will add to the Hamiltonian this term over E. So I'm gonna, for this will be clear later on that it will correspond to the vertex term of the string net model. But right now I'm gonna just call V, these triangles are labeled by V. And it's just a product of the ZZ terms, of the mu Z terms on each of these three links. And so you want the product of these guys to be 1, so there's no gauge flux piercing any of the plaquettes.
Just lift up board up the type of for the bottom.
Okay. Maybe I want you to see all 4 steps though. Okay. So now we can easily do all those procedures with H1 and H2 and see what we get. Let's first start with H1. Initially, our Hamiltonian.
Question?
Yeah.
So the mu acts on what?
Yeah, we have added additional degrees of freedom on the links,
Okay.
and these are going to be Pauli operators that act on the 2-dimensional local Hilbert space on each of those links.
Each link gets a C2, and these are just Pauli matrices.
Yes, exactly. Yeah. Okay. So using our Gauss law, we can replace the xb by a product of mu x's around a vertex. So we're going to have H. I'm going to, where this BP is kind of this operator here. And then we also have our zero flux term, which looks like this. Okay, And now we can immediately read off the anyons, or the spontaneously broken one-form symmetries. So you can see that in this lattice, there's actually going to be Z2 times Z2 spontaneously broken one-form symmetries, which correspond to the anyons of the Tor code. There are 4 kinds of string operators. One is just a trivial string operator. Now, if you act with a mu z, you create 2 of these charge excitations. So if you act with like mu z here, then you create a charge excitation here and a charge excitation here because it anticommutes with this BP term.
Sorry, that's a good question. Are there 5 or 6 UXs?
Sorry, yeah. So, and these are topological because now you can move these guys. You can kind of, you have string operators on the direct lattice. So I can act with a mu z here. And that will create 2 charge excitations here and here. So you have mu z, string operators. And this creates your charge excitation, excitations. You also have mu x, where if you act with a single mu x here, then it will create 2 flux excitations, this one and this one here. So you also have mu x string, and this will give you your flux. So these are your 2 one-form symmetries. They're topological in the ground state. So as Sal mentioned, there's some subtleties with lattice models in the sense that these one-form symmetries are not topological in your Hamiltonian. However, they are topological in your ground state. So you can smoothly kind of deform these operators, these closed loop operators in your ground state. And then, of course, you have the composite. So this is going to be, if you have E and M fused together, then you have your fermion. So, and the nice thing is, now what you can see is, if we go to the dual lattice, so if we go to the dual lattice, then we'll have a dual lattice that looks like a hexagonal lattice. And now on this dual lattice, this BP operator will just look something like this. And the AB operator will look something like this. And in Lorenz's talk, he mentioned how a stringnet model has an AB term and a BP term. What the AB term does is it implements the correct fusion rules. So you input a fusion category, and that what the AB term is, it acts on these trijunctions and makes sure that all these trijunctions satisfy the fusion rules of your input fusion category. So you can see now, you can consider this is a 2-level system. So mu z is equal to +1. We can take that to be like the trivial string operator, or trivial element of a Z2 back Z2. And then mu z equals -1, that's kind of the non-trivial element of back Z2. So I can call that like non-empty and empty, or occupied or unoccupied. And so you can see that now this AB term, what it does is it makes sure that at each of these junctions, you have 2 of these non-trivial elements of your VEC-Z2 fusion category. And what that implements is exactly kind of the VEC-Z2 fusion rules, right? Because the non-trivial element fuses with itself to give you vacuum. And so you can see that this is precisely kind of the stringnet model when you input kind of a VEC-Z2 fusion category, where this is the implementing the fusion rule. you can also show that that BP operator is very simple, and that's because it would be what you get. So as Lorenz probably wrote down, the BP operator is this big product of F symbols. The F symbol for this vec C2 with trivial F symbol is just trivial, and that's kind of the operator that you would get. Okay, so now we also have H2, so let's implement gauging on H2. H2 has a bit more complicated a Hamiltonian term. So so initially our Hamiltonian term looks like the x operator at this vertex, but you have all these I to the 1 minus z operators on each of these pairs of lengths. Now, with our minimal coupling procedure, we change these pairings to something like this. So it's a three qubit coupling on each of these lengths. It will be convenient to do a unitary transformation that kind of maps this is a local unitary transformation. The Hilbert spaces are isomorphic, and the purpose of it is to just kind of decouple the matter degrees of freedom. You can also think of this as a gauge choice. And you can see that these have the same commutation relations as you would want because it's just a unitary transformation.
Another stupid question is BP, is it supposed to have an X in the center?
No, so this is just acting on the gauge degrees of freedom. And it doesn't have an X in the center because we've used the Gauss law to replace the X with the product of. Yeah. Yeah.
And in the Joule lattice, should I think of BP, should I think of it as being around a hexagon in the Joule lattice as well?
Right, so this BP operator is around a vertex on the dual lattice.
Yeah,
It looks like.
constant with that.
Yeah. So that's why I labeled it BP.
Yeah, okay.
Okay. So once you do this transformation, this coupling on the links kind of simplify. So now all you have is something like this. So it's still kind of a complicated operator. It has a mu x on these 6 links, and it has an I to the 1 minus mu z on these 6 links. But okay, it's an operator. It's and it lives on this plaquette here. So now you have this guy, which I'm going to call, maybe I should call this BP1 and AB1. Where the AB terms look the same as with H1. And again, you can look at this on the dual lattice. So on the dual lattice, it would look something like this. So again, you have the x's along these lengths. And then you also have legs kind of emanating off, which have I to the 1 minus mu z. So this is what it looks like on the dual lattice, which is typically what the BP operator looks like for a string net model. The AB operator looks the same. Okay, so what are the excitations of this lattice model? We can similarly look for these fluxes and charges. So again, you can create the charge using just a mu z, right? So mu z string. All the mu z string does is it anti-commutes with this BP operator, but it commutes with this AB. So it only creates an excitation labeled by a -1 eigenvalue under BP. However, the flux strings are much more complicated. And one way to see that is if you wanted to excite this AV term, then you might try to do the naive thing that we did down here, which is just act with a mu-x string. However, if we just act with a mu-x string, that also fails to commute with this new BP term. So that is not our flux operator. Oh, I should also mention that you can also see, because this is poly Z and poly X, they have anti-commutation relations that reflects their -1 braiding. So I'm not going to write down the string operator for you. It's a bit more complicated, but you can work it out in this lattice model. And it looks kind of reminiscent of that guy that we wrote up there. You need to kind of construct the string operator such that it only violates this AV term and not this BP term, which is why it's more complicated and we can't use the naive one that we had previously. So then we also have a complicated which gives us our semi-line. And if you work out the explicit model in all the gory details, you can compute the self-braiding and show that it gives you this I that you wanted. Okay. I should mention that the reason why you still have the same E, which is the violation, which is the same charge, is because, as we saw, that's related to the fact that the only thing that's changed are the F symbols. The fusion rules are still the same. This comes from back Z2 with trivial 3 cocycle. This comes from back Z2 with non-trivial 3 cocycle. So the fusion rules are still the same as before, and that's related to the fact that this still has the same charge as before. It's just the flux, the BP term looks different because the AV term implements the kind of fusion rules, and the AV term is the same between these two models. Okay. Any questions about gauging on the lattice in these two models? Yeah.
Is there a physical picture of what it looks like if a topological order goes to its gauged version? Like, can you physically do this, or is it just a completely different theory principle?
Are you asking about, like, if you try to tune a phase transition?
Yeah, because like in high energy, for example, if you gauge U1, you have a dynamical electromagnetic field suddenly, which was before the background field. So is that like in the story?
Certainly, there's kind of confinement-deconfinement transitions that you can tune. So we know of like what they are supposed to look like in the simplest case of like ZN gauge theory, confinement-deconfinement transitions. I don't know of any analytic results and very few numerical results about confinement-deconfinement transitions for more general kinds of topological order, even for finite group gauge theories, which you might have thought have been studied, but I don't think they have really been.
Sorry, can I just ask again, more stupid questions? You have some equation there, ZP, UZP, equals UZP, where did that come from? And the equation below it. What did it
Yeah, so one way to concretely implement this is you can just do a unitary transformation on your system, like a local unitary, just to kind of decouple the matter degrees of freedom by the capital Z's. You can also view this as like a gauge choice where you've integrated out the matter. And so now you just have, you can just set these ZPs to 1 after doing that unitary rotation. But this is like completely equivalent to each other, right? Because all the commutation relations, everything is the same. So it's kind of just like a different frame that you're looking at the picture in. Okay.
What are you going to describe on the lattice the inverse procedure going from the Tor code back? Is that something?
Yeah, you can also gauge one-form symmetry. I'm not going to describe that today. Sal is actually going to give an example of gauging one-form symmetry, but they're going to do something a bit even more complicated, and they're going to do higher gauging of one-form symmetry, which, yeah, in the tutorial later tomorrow. But yes, you can also do gauging of one-form symmetry, and you get back like a dual zero-form symmetry. Okay. Good. So I should mention that, okay, so in yesterday's tutorial, we learned that there are topological symmetries when for higher form symmetries, if you have a non-tensor product Hilbert space. Generically, in a tensor product Hilbert space, you get something non-topological, but it acts topologically on the ground state. So what that means is that you have these operators that act on contractible loops, but they're still non-trivial operators in the Hilbert space. In most cases where we study spontaneous symmetry breaking of one-form symmetries, they're not actually symmetries of the Hamiltonian at all. So in most cases when we study So in most cases where people find topological order, spontaneous breaking of these one-form symmetries in the world, there's no actual symmetries of the Hamiltonian, so there are no string operators that commute with their Hamiltonian, even the contractible strings. Nevertheless, they emerge at low energies. So what I mean is, even if this doesn't commute with your Hamiltonian, it can still be the case that W of gamma on a ground state gives back the ground state. And these guys can be topological in the ground state. So what you can show, so yesterday when we introduced the notion of gap phases of matter, we said that two gap phases of matter are in the same, realize the same phase, or two gap Hamiltonians realize the same phase if you can interpolate them while maintaining the gap above the ground state. So maybe this is 1, this is 0, and this is some parameter s. And it can totally be the case that as you turn on an infinitesimal s, none of these line operators commute with the Hamiltonian anymore. But what we also mentioned yesterday is that if you maintain the gap above the ground state, then the ground states are unitarily related. So omega I equals u omega I of 1. And so what you can show is that even if the Hamiltonian doesn't commute with these symmetries, then generically if you maintain the gap above the ground state as you do this interpolation, you can find dressed string operators that actually kind of stabilize the ground state and act topologically there. And this is the generic case that you have in condensed matter settings and lattice models. It's many times we have emergent symmetries in the IR that don't show up in the UV. And so in these particular string net models, they're particularly nice because these one-form symmetries, like these Z loops and these X loops, and this also has one-form symmetries, Z loops and more complicated loops. These are exact in the sense that they commute with their Hamiltonian, but that is kind of a very finely tuned point in this phase diagram. And there's kind of a recipe for how to get this unitary and ensure that it's local when you maintain the gap above the ground state. Okay, so in the remaining amount of time, I'm going to now talk about the gap boundaries of these two topological orders and show that is sort of related to the anomaly at the boundary that we started off with when we first talked about these two paramagnets. Okay, so as we mentioned before, This H1 gauge is this torque code model, and this H2 gauge is this doubled semi-on or twisted Z2 gauge theory model. And they differ only in their braiding. So they have the same number of, they both form Z2 times Z2 1-form symmetry. It's just the braiding is different between the two. And in this case, they're abelian topological orders, meaning all the 1-form symmetries are actually invertible. And so we can enumerate the gap boundaries using Lagrangian subgroups. So earlier from Niels, you guys learned much more complicated symmetric Frobenius algebras, but for invertible 1-form symmetries, we can just work with Lagrangian subgroups. And we'll use these two examples. So a Lagrangian subgroup, Gn subgroup. So a Lagrangian subgroup, so when you have invertible 1-form symmetries, then the 1-form symmetries just form a group. And a Lagrangian subgroup is a subgroup of that group, such that the size of the subgroup is equal to the total quantum dimension. So this is your modular tensor category. Which is equal to 2 in both of these cases. And it's a subgroup that consists only of bosons. This implies two properties of Lagrangian subgroups. One property is that they all have trivial mutual braiding. And you can see this because you have this formula. Well, all these guys are 1 because they're all bosons, so this has to be trivial. The second property that it implies is that for any A not in the subgroup, there exists V in your subgroup such that it detects your anion. So everything that isn't in your subgroup gets combined. This follows from braiding non-degeneracy. You can imagine that if you have, so you can derive this from braiding, assuming braiding non-degeneracy on your braided tensor category. And so the Lagrangian subgroups label the gap boundaries of your topological order. So when you have a gap boundary of a topological order, you also get a symmetry. One way to see that in a very simple model is to consider the torque code with so-called rough and smooth boundary conditions. I think Lorenz had this Kong-Kataev paper in his recommended references. So for simplicity, we can consider the torque code on a square lattice. And if you have the torque code on a square lattice, then this is the so-called rough boundary condition. And what the rough boundary condition does is it looks like the same as your usual torque code Hamiltonian. However, these plaquette terms are truncated. And because these plaquette terms are truncated, that means that suppose I had an E excitation, like way out here at this vertex. That E excitation can be moved to the boundary by a string of Z's. poly Z operators. And you can see that this polystring operator can move this E excitation and annihilate it at the boundary, and it commutes with all the Hamiltonian terms near the boundary. Right? It commutes with this vertex term, and also commutes with this truncated plaquette term. And so what it means is for the rough boundary, and this is like Dirichlet boundary conditions for your Z2 gauge theory, E and maps to the vacuum, 1 maps to the vacuum, M maps to M, and EM maps to M. And this is because the M excitation, the flux gets stuck at the vacuum. So it can't be annihilated, and it gets stuck there. And what you can also see is that along this boundary, there is a operator that isn't generated by any of these local terms. This operator is just a big product of X operators all along this rough edge. And so this can be thought of as creating two M excitations and those can be interpreted as symmetry defects of a zero form symmetry in 1 + 1D. And if you wrap them around, then you get a zero form symmetry operator in the 1 + 1D boundary. And that zero form symmetry operator is a Z2 operator. So this gives you a back Z2 with trivial 3 cocycle. And then we can consider our system with two boundaries. So this boundary will be rough. So this is this boundary is rough, and it realizes back Z2 with trivial 3 cocycle. And the important thing is, as all of you probably know, with Torco there's another gap boundary because M is also a boson. So even if you condense 1E here, you can condense 1 and M on the other side, and this gives you a 1D theory that has no spontaneous symmetry breaking and is gapped. And it has no spontaneous symmetry breaking because there are no local order parameters. So if we chose this to be E, then you have a local order parameter given by the E world line. But we can also equally well choose this to be 1 and M condensed, and then you don't have any order parameters. So this has a unique ground state. It's gapped, symmetric, and it realizes a trivially symmetric phase, indicating that this topological order came from an SPT who came from a trivial 3 cocycle and had a gapped boundary, symmetric gap boundary. Yeah.
Can we impose this condensation using like a time in Hamiltonian or something?
Yeah, so you can do kind of condensation in the bulk in terms of getting to a trivial theory. In this case, we're just implementing it in terms of a choice of Hamiltonian terms for the boundary, in terms of an edge theory.
So I just need to ask, what did they look like?
Oh, yeah, so here is this rough boundary where the Hamiltonian terms at the edge look like the usual AV term, and you also have a truncated BP term.
Oh, okay.
Yeah. And then on the other kind of boundary, if you had a smooth boundary, instead you could have a truncated AV term and the usual plaquette term.
And that'd be the 1M group?
And that will do the mapping of, so if I did smooth, then you would map E to E, 1 to 1, M to 1, and EM to E. Okay. The crucial thing then is, as we saw, the 3 cocycle gives the semyon non-trivial self-statistics. So it's no longer a boson that can be condensed. And so what you get, if you try to do the same thing with the semyon theory and look at its gap boundaries, you still have the same gauge charge, so you still have this gap boundary, and you'll find that the symmetry that's realized there is related to now the semyon world line instead of this trivial kind of flux world line. And that will give you Vec2 with a non-trivial 3 cocycle. And in that case, because this boundary no longer exists, we always have to put the 1e here. And so you always have spontaneous symmetry breaking if you have a gap 1 plus 1d theory. And so now we've seen from many, many different perspectives how the anomaly of the 3-Co cycle manifests in these two different kinds of paramagnets. From first starting from their edge theories, then going to their symmetry fluxes, then going to properties of the anions that you get from gauging them, and then going to the gap boundaries of these topological orders. And then in the next lecture, I hope to talk about string net models more generally, not just kind of G-gauge theories, but in general, how do you go from an input fusion category and having a mechanism as a physicist to really kind of compute the anion types and get the Drinfeld center and get a Hamiltonian and get a ground state wave function and all those things that you can now, if you wanted to, you could even put on a computer. Thank you.
More questions?
So for the gap boundaries, like a codimension 1 defect. And I guess in the third code, we also know that the codimension 2 defect is dimension 1. You have any comment on how the idea of gauging
So are you talking about the invertible defect that permutes E and M?
Yeah.
Yeah, so that was related to higher gauging that Sal will talk about tomorrow. Not exactly that example, but they'll mention that example. Yeah, so here we gauged a zero-prime symmetry in all of space, but you can also gauge other symmetries in submanifolds, and those can be used to construct these invertible and non-invertible defects.
Oh, I guess another question is, I think in some literature, people talk about codimension 1, codimension 2, but some people also mention something called distinct. Is it something you also think about, there's some simple way to understand?
Yeah, so in 2 plus 1D, right, we had not only the symmetry defect, but we also had the symmetry flux that the symmetry defect ends on. So if you try to do the same thing in 1 plus 1D, we had the symmetry defect, but now it's a bit weird, right, because the symmetry defect is 0D. But then if you look at space-time, you can still end it on something, and that would be like an instanton. The problem with that is I don't really know how to implement that as an operator, like implement that. So here, for example, with the symmetry fluxes, we knew how to modify the Hamiltonian to insert these extrinsic fluxes. And I don't know how to do that for like an instanton, but that would be kind of the intuition of what it would be.
Sorry, I think I just forgot about this. Can you remind me how the E particles of like the toric code? I just did not get to myself that why it was stuck at the rough boundary of.
You mean for the smooth boundary, why it gets stuck?
Yeah.
Right, so for the smooth boundary, you can see that if you had a flux excitation, say here, then I can move that flux excitation using a string of, maybe I shouldn't put X. I can move that flux excitation using a string of X operators to the boundary. And this string of X operators commutes with all the boundary Hamiltonian terms. However, if I have an E excitation, then then it doesn't commute. Like I can bring it to the boundary, but it won't commute with all the boundary Hamiltonian terms.
So we start from the E at the edge and then try to propagate that inside the block.
What I mean to say is that like when you bring an E anion to the boundary, it doesn't get annihilated at the boundary. So it has to kind of just stay stuck there.
Oh, okay.
Yeah.
Anything else? Would it be possible to write an example of a gapless boundary?
Yeah, you can tune the boundary to be gapless. It's just more subtle in terms of, like, for the gap boundaries, we can kind of have a systematic way to write them down and ensure it's commuting, everything is gapped. Of course, you can also add whatever you want to the boundary to make it gapless as well. Like, yeah, you can add whatever you want to make the boundary gapless as well. It's just less under control.
I see.
That's it.
If I wrote some random operators on this edge and I got lucky, there'll be a gapless.
Yeah, or you can try to like tune between two gap boundaries to get something gapless.
Okay, let's thank Carolyn again.